name is Dan Kerns. I run the Rook project. I happen to also work for Quantum. Today what I want to do is talk to you about how, by leveraging an environment like Kubernetes, you can orchestrate very complicated storage systems and save yourself a lot of work, consequently focus more time on building storage systems than on building distributed computing systems. I'm going to give you a demo of Rook running on Kubernetes, and I'm going to talk to you about the architecture or some of the architecture that we use inside of Rook to support Ceph on Kubernetes. Okay? So I think everybody understands. I'm going to fall off the stage here. I think everybody understands that storage systems, distributed storage systems, are really complicated distributed systems. There's all kinds of stuff going on. There can be thousands of instances of different process types. There can be thousands of nodes. They're actually very complicated systems. And storage developers spend a lot of time working on the life cycle of the various processes and daemons and things like that that support the storage systems. It's a common cause of failure. It's not just about the data structures that represent the storage. It's about keeping the system alive and healthy. And that's where Kubernetes comes in and makes an enormous difference. So in a Ceph system, there's probably 10 different services, maybe more than 10. Thousands of instances of those services in the storage cluster. You have to keep track of them all, you have to manage the life cycle, and you have to do what you need to do to keep them all healthy. Kubernetes, I don't know how much people know about Kubernetes. Kubernetes is one of several container orchestration systems. The goal is to drive up the utilization in cluster computing systems and to move to a more declarative model than procedural model for managing the various applications that run in the system. It's got all kinds of features. There's lots of goodness. It seems to be picking up steam in the marketplace. At Quantum, we're firm believers in Kubernetes. And so we looked at how we could use Kubernetes. We make storage appliances, and so we looked at how we could use Kubernetes to make the job of building a storage appliance easier, and how we could ultimately build a higher quality, more reliable storage appliance with Kubernetes. The thing that really jumps out about Kubernetes is the declarative nature of what you do. You generally don't write code to tell Kubernetes what to do. You basically write a spec. This is what should happen. I should have 3 instances of this application running in my cluster. Kubernetes goes and makes sure that constraint is valid at all times. There will always be 3 instances. So if one of them dies for whatever reason, a new instance is created. Likewise, you can say, I want to have enough instances so that my response time of my application is such and such. And Kubernetes will do the scale up and scale down and whatnot of that application for you. There's also a bunch of support for the deployment of applications to nodes. If you ever built a system like this, the deployment, it's the simplest thing in the world, except that it's not, right? And there's actually a lot of trouble that goes into deploying applications in distributed systems. Kubernetes actually makes that simple. And likewise, updates. When it comes time to update that application, you generally don't want to take your service offline. You generally want to have some sort of online update plan. But of course, those are hard to build. And again, Kubernetes has platform support for doing those kind of online or rolling updates. There's several different strategies. And of course, in order to do all this, it's monitoring the health of the system and whatnot. So there's a great deal of information available about the health of the various applications that are running in the system. So I sort of mentioned the declarative thing. It supports lots of different service models. So you can have a service model. I talked about N instances and load balanced instances, but there's all kinds of different service models. And there's this concept of a thing called a pod, which is a collection of services that work together. And so you can put a bunch of services in a pod, say microservices, and they will be scheduled together. It has an extensible control plane. This is one of the biggest things that's a benefit for us. In the current version of Kubernetes, these things are called CRDs. And you define CRDs and can interact with a control plane through these CRDs. And it provides complete application lifecycle support, which is a great deal for the storage cluster because it has to run forever. Now let's look at storage in Kubernetes. So if each one of these vertical things is a node in Kubernetes, you may have some number of applications running on these nodes in whatever layout is necessary for that application. The way storage is handled in Kubernetes is it's handled off cluster, or the normal way it's done in Kubernetes is off cluster. This is through something called a persistent volume claim. And if you look at the Kubernetes documentation, you'll see it says it does storage orchestration. What that means in Kubernetes speak is that if this application is connected to some storage out here, and then that application happens to be rescheduled on this node, the volume attach points will be moved to that other node seamlessly, and that application can continue running. So if it dies here and it's rescheduled there, or if it's rescheduled in multiple places, Kubernetes will handle that transition for you. And that's actually pretty cool. In Rook, so Rook is an open source project that we sponsor at Quantum. We have lots of contributors. You should go to GitHub to check it out. Our idea is, gee, what if we actually brought the storage system into the cluster? What if we ran the storage processes inside the Kubernetes cluster? This gives you a lot of flexibility. First, it means you don't need to have that external a separate storage box that you bought from somebody else. You can use disks attached to the various nodes in the cluster. But it also means that the applications that make up the storage system can benefit from all this goodness that I've been talking about with Kubernetes. I think that's one of the major benefits. So we orchestrate Ceph in Rook. Rook isn't exclusively Ceph. We'll do other storage backends over time. But Ceph is interesting for tons and tons of reasons, and there's been quite a number of Ceph talks at this conference. All of those apply here. We have a pod called the Rook operator. And you can think of it as a system operator or something like that. You could think of it as the operator pattern if you're familiar with that. But the idea is to manage the storage cluster. And so there's a bunch of code in the Rook operator that manages the lifetime, uses Kubernetes to manage the lifetime of all the components that make up the Ceph deployment that sits underneath Rook. And deploying Ceph is actually pretty complicated in practice. And so we try to abstract away a bunch of that and more directly integrate Ceph with the Kubernetes platform in the process of doing this. And I'll demo this later on. And so because storage now runs in the cluster, you as either an IT person or as a developer or as a vendor, in our case, have the option to do either a converged or an appliance model for your storage. So you can build a Kubernetes cluster where the applications and the storage all run together in the cluster, and that has certain benefits. Or if you're building a standalone storage device, you can just not have any applications running except the storage application. So it gives you quite a bit of flexibility in how you end up deploying the storage. So our architecture looks a little bit like this. Same picture as before, except the Rook processors are running throughout the cluster. What we get from Kubernetes, on the other hand, is support for all the things in this box. And some of those things are pretty hairy. Like I mentioned, the upgrade and the deployment, but also things like security and scheduling of these processes. We're using Kubernetes Security for controlling access to the cluster in this case. And so we're hiding the Ceph level. Ceph has its own security system. And so we're hiding that because for a Kubernetes user, they already have to deal with the Kubernetes security. What do they want to deal with the Ceph stuff for? Okay. So we think this is a really big win. The components of Rook, we have the Rook operator I mentioned already. The various Ceph components, I just listed 5 of the major ones. In some configurations, we have storage presentations in NFS, CIFS, and iSCSI. We have the Rook agent, which is a Rook component that runs on every node in the cluster that handles persistent volume mounting. And the Rook API, which is it just presents a RESTful API if you're not using the Kubernetes CRD extensions. And I'm going to go into each of these and sort of talk about how they're managed a little bit differently in the Rook cluster. So first off, the operator, the Ceph manager, and the Rook API are pretty much singletons. You generally run one instance of these guys. You may run 2 instances or 2 or more for high availability, but it's a master-slave relationship. You'll fail over to the other node if you need to. So they're very easy to manage in the Ceph environment. As a cluster comes up, we bring up the Rook operator, And then we support multiple Ceph clusters on a Kubernetes cluster. So then you'll specifically, after you bring up the operator, you'll specifically say, I'd like to create a Ceph cluster named, Joe, right? And then it goes ahead and spins up the Ceph daemons. The Ceph monitors are a real problem area for Ceph clusters. The Ceph monitors are they control the Ceph cluster in a very, very real way. There have to be at least 2 running at all times. In our environment, we only support 3 because we never saw a need for more than 3, but you can have any odd number above 3. And the monitors maintain a quorum, so they're how we detect, they maintain this. Each maintains a copy of the state of the cluster, and there's a quorum algorithm underneath that has to run. And so it's really important that we run just 3 of these, and that their names are really well known. And so one thing that happens in Kubernetes is pods can get rescheduled over time. A node fails, or it dies, it crashes, whatever happens. It can get rescheduled. And Ceph mons don't tolerate having their IP addresses changed very easily. And so you have an option where you could say, okay, mon number 3 died, and so I'm going to create mon number 4, and we're just going to write off mon number 3 forever. But what we actually chose to do is if mon 3 dies and gets rescheduled on another node, we're using Kubernetes service IP addresses so that the IP address remains consistent regardless of where in the cluster the mon comes up. That turns out it's been really, really productive for us. Everything in a Kubernetes cluster has to be able to fail, and that includes the mons. And so we've spent a great deal of time here understanding failure in the cluster and understanding how we recover from failure in the cluster. The Ceph OSDs, the basic idea is most people run one OSD per disk drive or per RAID controller or something like that. We generally don't use RAID controllers for obvious reasons. And so we'll schedule a pod on every node, and each pod will contain however many OSDs are necessary to support that node. So if there's, say, 10 physical spinning disk drives, there may be 10 OSDs in that pod. But we also have the ability to redirect metadata to other nodes, to other devices. And so if you say I have an SSD and you want to store your BlueStore metadata on SSD and your BlueStore data on a spinning disk, that would be one OSD, and we can manage that declaratively. It's important. It's really surprising to people who have used Ceph before that there's no Ceph.conf files here. I mean, they do exist under the covers, but nobody who uses Rook ever sees these files. They're generated on the fly by Rook, and they're put in the right places in the pods. And so the Ceph daemons can run unmodified, but nobody ever has to edit a Ceph.conf file. For the other services, RGW, which is the object store, and MDS, which supports the file system, we scale as needed based on traffic. And so the startup and shutdown time of these services, particularly MDS, is they take a long time to start up. And so you can handle, there's parameters that you can use to control how often they're started up and at what the transition point is and so on. We have the opportunity to do SSL termination at the Kubernetes load balancers if we want, instead of terminating farther inside the Ceph system. So that actually simplifies a bunch of the deployment and configuration of Ceph. Okay. So what do we get from Kubernetes? Again, this life cycle, it's a really big deal if you built a distributed system. Just processes dying, right? You don't want to wait to find out. And we get this lifecycle support at both the node, pod, and process level. We have automatic failover of services. Kubernetes remaps IP addresses and makes things look fairly invisible for that. Support from Kubernetes directly for upgrade and for rolling upgrade. We can control it, or we can let Kubernetes do it in its own way. The cluster level metadata, I mentioned the Ceph.conf files that Ceph uses. Our metadata is ultimately stored in etcd because that's the way you do it in Kubernetes. But we're generating configuration files on demand for each of these services based on what users have asked the cluster to do. Secrets. Kubernetes has support for secrets built in. Just basically think of it as encrypted things that you don't want other people to see. We use Kubernetes secrets to store the Ceph secrets. So the Ceph keys for Ceph encryption and that sort of stuff are all stored in Kubernetes secrets. So again, we're leveraging the Kubernetes authentication and access control system to manage the Ceph secrets. So when I'll demo, you won't see any of that. And it has an extensible API. So with that, if there's questions, I could take them right now, and then we can jump into demo maybe. Yeah.
So not specific to Rook, really, but in general, let's assume we have a persistent volume in the Kubernetes.
Mm-hmm.
So it's mounted on the host.
Yes.
Right, and then you give access to it from the container.
Right, there's a container that's running by the pod.
Here is just what thoughts are about multi-tenant workloads are in the same Kubernetes cluster. How do you ensure that another container does not, or somebody else on that host doesn't have access to the persistent volume related to your container?
Well, once the volume is mounted on the host, access to that volume is controlled by Unix access controls, right? And so Kubernetes ensures that no other container has access to that mount point.
As long as it's not running as well.
As long as it's not what?
As long as the container is not running as well.
It's not what?
It's another container or another process on the host that is not running with the root privileges.
That's right. And running with root privileges, yeah, that's... Okay, let me demo this thing. So hopefully the demo gods are with us. I don't even know how I do this with the projector. Here we go. Let's... Oh, you've got my screen, great. So here I have a Kubernetes cluster. I need to make it bigger, right?
Would be helpful.
Yeah. It's not supposed to be an eye chart.
From here.
Okay, I'll make this one bigger too because we're going to get over there. So I have a Kubernetes cluster. It's got 3 nodes running, fairly generic cluster. In this window over here, I'm going to run this watch script. That just runs watch over and over in the window and makes it easy to see what's going on in the cluster. So again, we can see that there's 3 nodes running. Currently, there's no pods being scheduled in the cluster, no persistent volume claims, and no services. And so if I go and create the rook operator, and I'll show you my cheat sheet here. I definitely have to cut and paste Kubernetes commands. So the rook operator has been created. So this YAML file has been essentially installed in Kubernetes at that point. This rook operator pod over here has been fired up, and that's all that's happened, right? It's just a process that's running somewhere, and it's not really doing anything. We haven't created a storage cluster yet, but that is what the rook operator does. And so we go over here, and we create a storage cluster. Okay, and I'll show you what this looks like. Thank God the same keystrokes work here. What this YAML file does is it basically says I want to create a cluster named Rook. Okay, I want to use all the nodes in the cluster for storage, and I want to use all the devices in the cluster. So you could specify a subset of nodes or a subset of devices. Basically, any Kubernetes selector here could be used to identify the nodes or the devices. In particular, I'm going to use the BlueStore storage system with a couple of parameters, and that's the whole cluster spec. And in the background here, we've installed Ceph, right? An entire Ceph installation, and so the monitors have just come up. There's 3 mons running on the 3 different nodes, so they have an anti-affinity, so they never run on the same node. In a couple seconds here, the OSDs and the Ceph manager will come up if we're lucky. There it is. So 3 OSD pods running on each of the 3 nodes. And each of those OSD pods, because I only have 1 drive on these VMs, is just running 1 OSD. But if there had been 10 drives on the VM, they'd be running 10 OSDs. So now all of a sudden an entire Ceph cluster is up. And I'm going to show you how it interoperates with Kubernetes, but let's look at the Ceph parts of it a little bit. I'm going to create this pod called Rook Tools. This is a toolbox pod that contains the Ceph command line tools, like the Rados command and Ceph and whatnot. And you'll see its schedule in the background there. And then I'll connect to it. And so I can use a Rook command line tool to have a look at the status of the cluster. Crossing fingers here, because it usually doesn't take this long. Okay, well that's not good. We can go Ceph status. Oh, it's a bad sign. Oh, there, I don't know, maybe it's slow. So you can get the status of the Ceph cluster. If I exit this and I go and create a storage pool, right here. Nothing much happens there. But if I go back to the tools and then I go, I think that. I don't know why it's so slow, but I created a pool with that command called replica pool. The process to create a pool, or the code to create a pool, looked like this. So in this case, I created a pool whose name was replica pool on the cluster, storage cluster Rook. It has a replication factor of 1, so not very interesting there, but I could have erasure coded it or whatever, and then I give it some more parameters to create it. What's really cool now, because it's Kubernetes, is that I can go and fire up applications and use the Ceph storage that's been created. So this is just a standard WordPress demo application. And I'll show you the file in a minute. But in the background here, you can see that a WordPress app and a MySQL app have come online. The MySQL app is connecting to that replica pool, that pool that we created. And MySQL is starting up. So let's have a look at that WordPress thing. Just very traditional Kubernetes YAML. We're going to create a service called WordPress. It's going to have an endpoint. We're going to create a persistent volume claim called MySQL PV claim. We're going to map that to the Rook storage cluster. We're going to fire up a MySQL instance. That's what this is, and telling it to use that persistent volume claim. And then we're going to move forward and fire up a WordPress instance. And so if we're lucky, we can actually come over and find out what port it's running on, 30542. And browse to that WordPress instance. 30542. Did I type it right? Somebody put www in there. Oh, is it? Okay, let's wait a sec. I think maybe when my laptop went to sleep, the Kubernetes nodes got sort of slow. Anyway, what else could we look at here? The MySQL and the WordPress descriptions are really very vanilla. Now, if you're building a storage appliance, if you're not interested in building a hyper-converged system, if you're just building a storage appliance, realize the run a storage system is a lot more than just running Ceph, right? You have a bunch of other applications running on the cluster, right? In fact, you have databases and other sorts of metadata running on the cluster to run the support applications for the storage cluster. So running MySQL inside the storage appliance is a very reasonable use case. And in fact, we're also running Prometheus and other things here. And so the ability to just declaratively say what you want through this kind of text is a super advantage. Maybe this would help. Ah, there we go. A little Wi-Fi changes everything. So MySQL is running, and then in a couple seconds, WordPress should start running. And the cool thing you can do once this finally starts up is you can tell that MySQL instance that, gee, I want you to reschedule another node. You can just kill it or something like that. And it will automatically, Kubernetes will pick another node for it to run on, reconnect the persistent volume claim to that instance. It'll still have all of its data. And the application, WordPress in this case, will continue working.
Inspect the pod, see if it's stuck on anything.
What's the magic for that?
kubectl describe PO. Yeah,
And then that.
and then the name of
I literally can never remember a kubectl command. What does it say here?
timeout expired, waiting for volumes to attach.
But it is bound according to the.
Would it,
Try destroying the pod and try to start deleting the pod and see if it comes back up. kubectl.
sorry. The WordPress pod, you think?
And now do another. There we go.
Boom. All right. Thank you. I hate doing live demos, but I also hate it when people
The IP address may have changed.
504 30542. There we go. And so WordPress comes up, and we can configure this. We don't need to save our password. And so there it is, WordPress is running. And then what I was going to demonstrate is if you go and kill the MySQL pod, which is currently running on node 2, so that pod's terminating, a new container is creating. Hopefully it'll work this time. I don't know why it got so slow. Something about running on my laptop. What was your magic command? Describe.
Was there a MySQL container on node 3? It might just be downloading the container image.
Oh, that's what's going on. I preloaded the containers, and but I might not have done it on every single node. I'm sort of concerned about why the one I killed is not terminated yet.
Sometimes they take a long time. I'm not entirely sure why.
in a perfect world, it would have just restarted and I could have shown it too, but the demo gods were not with me. So that was the demo. There are some disadvantages to this approach. First off, we don't own the whole software stack. And if you're a storage systems vendor, that could seem like a big issue to you. And this particular stack, the Kubernetes stack, is evolving really, really quickly. Kubernetes is on, I think, a 3-month release cycle. Maybe it's even less than 3-month release cycle. And so every time you turn the page, a new version of Kubernetes is coming out or something else is changing in the stack. And again, things changing that rapidly in a storage seems to be somewhat incompatible with the storage system. So we really don't have total control of the stack, which is not what storage vendors generally look for. The flip side is that by delegating all this work to Kubernetes and giving it all this and leveraging it for all this work, it's an opportunity cost argument, and we have a lot more time to implement storage features, which are the ultimate features that we think our customers are paying for. And so the net here is that Kubernetes turns lifecycle code into lifecycle declarations, so we can write these declarations that are much easier to do than to build the code to do that. And we have more time to spend on logic for the storage system. Operationally complex systems like Ceph can be dramatically simplified through tight integration with things like Kubernetes, with patterns like the operator that we use. And we believe that overall systems reliability is increased. So, any questions? My shameless plug, but any questions? All right, thanks a lot.